I've lost something.
But you always, all the approximations are in little d.
All of them are in little d. So all the planes that I construct here are in little d dimensions. And it turns out that these details can also be chosen to be little d dimensional. It's not obvious, but almost. And so in the end, you get X represented as a small d dimensional projection plus a correction, plus a correction, plus a correction, and so on.
How do you choose little d from capital D?
So in the statement of the theorem, I assume that the small d is given to me. It's known to the algorithm. In practice, we've done a lot of work, some of which I described yesterday by doing what we call multiscale SVD, to detect the small d very, very reliably. Yeah, so here I'm saying that as if we know small d, but I claim I have good reasons for knowing it because we've done previous work.
It's an input of the algorithm. Right?
Yes. Yes.
I didn't understand how you choose the components, the points. Can you?
VCJ case? Yeah. Oh, so I didn't say that, and it's in fact absolutely crucial. Yes, so VCJ case should really look like DIADQ. So the condition that we have, and again, I have slides that I'm skipping in the presentation. I deleted them because I didn't want to be too technical, but VCJ case must have some crucial properties. The diameter should not be larger than 2 to the minus j. I want to think of them as blobs of size about 2 to the minus j, formally. The diameter is no larger than 2 to the minus j. Each of these contains a ball of radius 2 to the minus j divided by 2. And therefore, each of these as a measure, pi, the probability measure that I have, charges these sets more or less like a ball of radius 2 to the minus j. Those are the sort of a crucial condition of the CJ case. It's important to construct them. I'm giving you an algorithm, and the guarantees are going to be on the algorithm that I use to construct the CJ case. And the algorithm that we use is a variation of the cover tree algorithm by Langford and others in 2001, 2003, I don't remember the exact date, that, you know, if you massage it a little bit, you can get it to produce CJKs that might have these properties. Now, observe that we did this construction originally in the continuous case, when you have the manifold. But we're going to have samples. So you get these samples, you run an algorithm, which, by the way, is highly nonlinear and complicated. You get CJKs, which are random. And you want to say that most of them, or with high probability, are going to have the right properties. And then the subspaces that we construct at every node are going to be random too. And you want to say, oh, they're pretty good, and so on. So in the proof of that theorem, we have to go through all these steps where we say that even if we run, this algorithm for random data, then with high probability we get good results. The theorem, what is the dictionary here? The theorem considers the following simple case. It says, if you fix a scale j, you have a bunch of small d-dimensional planes that sort of approximate your manifold. Okay, so the set of phi jk's, varying k for a fixed j, is your dictionary. The encoding map is simply mapping each point to the closest plane. That's the encoding map, and the decoding map is just the projection. We just apply the adjoint. So the only question is, how do you choose j, right? If you choose, the algorithm has to choose j. And if you chase j up here, you're using only one plane. Your dictionary is going to be really small, but probably you're not going to have accuracy because one plane does not approximate your data manifold well. If you choose j very large, you're going to get really good accuracy. But what is the drawback? The drawback is that if you go down the tree, each of the nodes have fewer and fewer points. And so the randomness down here is much, much larger and out of control. And so the theorem is essentially going through the tree and says, oh, I want to go down the tree, but I should stop when things become too random and too unreliable. I stop there. What can I guarantee? Which kind of accuracy can I guarantee? And that's where the theorem comes. Yes?
So in this multi-resolution schema, the patches found by Olhausen and Field are in the top or in the bottom?
Okay, so in that case, you would have all the patches. That's your point cloud in high dimensions. I forget the size of the patches, 8 by 8 or 16 by 16. Say 16 by 16, so the capital D was 256. And all the patches were at the top. Then the set of patches gets divided into two sets of patches, according to the cover tree algorithm. or 2. 2 is, it's really 2 to the small d. So it gets divided, and there are some patches here and some patches there. And then some patches here, some patches here, some patches here, some patches there. And in each of them, a dictionary is being constructed, and in fact, then an optimal scale is being picked. And the set of vectors in these low-dimensional planes is our final dictionary. So this is pictorially what happens, right? So you have all your points in a plane, and then you split the points, and you get 2 planes, 4 planes, and more and more and more and more of them. So, toy examples. If the data is on a very simple manifold, this is a Swiss round manifold, 2D, we embedded it in 100D. And here are 2 approximations to the manifold, using a scale 4, using 16 planes, and a scale 7, using 128 planes. And the data on this Swiss round gets compressed in what we call a geometric wave transform. Every column here corresponds to a point on the manifold. And this is a set of coefficients. At the top are the coefficients onto the top on the plane corresponding to the top of a tree. And as you go down, you're encoding the coefficients onto these difference planes, these geometric wave planes. And you see that lots of coefficients become 0, represented by white, very quickly. And in fact, we can predict how quickly they decay based on the smoothness of the manifold, and they decay second order. So this is a trivial example, but just to say, in the manifold case, it does what it's supposed to do. Now you can pick handwritten digits. This is an original picture. These are its approximations and multiple scales in this decomposition. This is the wavelet table of coefficients for 5,000 ones, I guess here. This is the decay of the coefficients. Here, these digits don't necessarily lie on a manifold. So one thing that we do is we choose the dimension the dimension small d adaptively, based on algorithms that I described yesterday. And we have a table where it's a table like this, where every column corresponds to a point, but instead of looking at the coefficients, we have blocks. At the top, we have a block, which corresponds to the one plane at the top of a tree, and we color it by its dimension, 4. And then we have more and more blocks. As you descend the tree, you have more and more blocks, and their dimension is always between 1 and 5. These pictures are in 800 dimensions, but all the planes that we construct in this fashion have dimension between 1 and 5, and they provide accurate representation of the digits. You can do it on faces. This is a Yale database of faces. We are in about 300,000 dimensions now, and you get approximations to a face. These are the multiscale approximations, the generic face. More and more details coming in. Finally, the mustache and the beard coming in, and then more and more details. Okay, so this is using maybe 5 or 6 coefficients every time you refine. These are some of the dictionary elements from coarse to fine. And these are the dimensions of the planes. In 300,000 dimensions, we use planes between 1 and 18 dimensional. But most of them really have dimension between 1 and 10. So what about patches? So people have been looking at patches of images for a while and use them in a lot of signal processing tasks. So you have a picture, you fix a value of small p, maybe 8 or 16, and you extract all pieces of the picture in squares p by p. That's what are called patches. And so you can do it from this image. You get a point cloud. Now this image becomes a point cloud in p square dimensions. If the image has n pixels, we get n p by p patches. Each of them is a p square dimensional vector. You can try to project them down, and here the red dots here are 2D projections of the patches from this image, and the blue are from this other image. And so you see structures in that space of patches, at least after you project. This has been used for image processing tasks. So here's one example. You could have a noisy version of a barbary image, and you could try to denoise it by averaging, by running nonlinear PDEs and so on. It's challenging, or doing wavelet denoising or curvelet denoising, but this is kind of challenging because of the texture on the trousers, on the scarf, and so on, or on the checkerboard on the here, which are high frequency information, which is often easily confused with noise. You can map this image to a space of patches and do denoising in the space of patches, and you get results like this. I don't know how much you can tell, and by this is by no way optimal. It's just a very naive algorithm for running the space of patches. But one thing that I want to remark is that one gets back the texture on the scarf, on the tablecloth. You get sharp edges, and on the trousers, almost for free by working with space of patches. This is something that it's much harder to achieve both if you use frame-based techniques by denoising in some wavelet curvature shear representation, or if you use PDE-based methods. Now, we did some work last year with some Gerber where, when we look at images, resolution matters. The size of the patches really matters. We know that for many reasons, both biological and from harmonic analysis. And so while people usually do this dictionary learning and signal processing tests on patches of a fixed size, one reason for that, I think, is because we were limited by computation. We just cannot do large patches. But we can. We could if we wanted to, but it turns out that that's not what I think one should do. So you can think that you can start from an image. You replace an image by the set of patches on that image, and then you build a dictionary for those patches. And then you could do it for patches of a different size. But now, the dictionary lives in a different space because the patches live in a space of dimension p squared, where p is the edge of the patch. So if you change the size of the patch, the space changes. But in fact, you can do the following. You can, and by the way, if you run it, if we do like Field's experiment, we get patches which look like the ones that he got, or everybody gets by now, no matter which algorithm they run. You can do the following. You can start with your image. You can create patches pj by pj, and pj might be 2 or 4 or 8 or 16 or so on. But then if you're looking at patches of size pj, you actually don't care about all the detail in those patches. When we look at a wavelets analyzing a scale pj, we convolve and downsample those patches. And we get patches of a fixed size. And so that's what one should really do, we claim. So you convolve these patches with a filter with pj divided by a fixed patch size, maybe the smallest patch size that you're interested in, maybe 8, and downsample. And whenever you do that, the patches, no matter how large they were, you convolve and downsample, and they become patches of a fixed size, p0 by p0. And so on those, you do the dictionary learning. And so we start with an image. We collect patches of all possible sizes, but the larger the patch, the more we smooth it out and the more we downsample it. And so we get patches which come from patches of different scales, but all have the same size. And we can do dictionary learning on those. And we get dictionaries which have orientation, localization. Some of them are nice and curved. Here is a training set, I think, so we can do it on natural images, we can do it on images, we can do it on toy images. For example, I think this was obtained by looking at black and white images of ellipses. And you get actually dictionaries which are a little bit finer than maybe curvets or shearlets in that they are curved elements, not just straight elements. And we get new families of transforms, which are multiscale. So you can start with an image. You can expand it on the dictionary corresponding to large patches. You capture the gross features of an image. These are two different ways of doing this transform. And then you look at the detail. You look at what you missed. You represent what you missed on the dictionary that you learn on slightly smaller patches. You capture something more. You look at what you missed. You expand that on dictionaries constructed on smaller patches. You capture more and more detail to reconstruct the image, guaranteed. So you get completely new families of multiscale transforms in the sense of multiscale on the image, okay, not in the multiscale in the space of patches. So I know I started 5 minutes late, but I'm going over time. So I wanted to mention something about extensions of this. So we're using now this sort of multiscale representation of point clouds in a lot of different tasks, different machine learning tasks, almost as a pre-processing stage. Data comes in, immediately gets compressed and sorted in this multiscale structure, exactly like we're used to do for, say, 1 or 2D signals in a wavelet or curvature shearlet basis. And then you can use this to do regression, classification, do crazy things such as approximating dynamical systems in high dimensions. And the one thing that I won't have to talk about, but that we used and that we're working on quite a lot is this estimation of probability measures. And let me just give you the basic idea. So this is what I called problem 2 before, where instead of just efficiently representing the data, I want to represent the probability measure mu. So given data, I want to construct a probability measure in the crazy high dimensional space that is close to mu. And the way we do this, and the way it's connected to what I said here is the following. We construct a tree sort of as before. Before, in every node, we were constructing essentially a small dictionary. Well, instead of constructing a small dictionary, we're going to construct a trivial probability measure. So I'm sitting at a node, and I look at the data in that node, and I try to approximate the data by something trivial. For example, a low-rank Gaussian. So a Gaussian probability measure, which is highly degenerate. It has a covariance matrix of rank small d. And I can ask, do I succeed? Well, maybe at the top node I succeed. That would mean that the whole data is Gaussian and low rank. That would be great. It never happens. But maybe it happens at this node and at that node. Or maybe it doesn't. And then I have to go at a finer scale. But so we're playing an multiscale approximation game in the space of probability measures. As we go down, our flexibility increases. We have more and more nodes, more and more little Gaussians that we can try to fit to the data. And we get better and better, provided we have enough data. As before, as we go down the tree, in each node we have fewer and fewer samples.